swarming E. coli bacteria, man-made vibrated particles, bird flocks, and schooling fish. These are all examples of active matter, but what is it that links them together? At a basic level, each consists of individuals with some control over their movement, sometimes composing larger groups. The ordered, chaotic, and even pattern-forming motion of active matter has long been studied, particularly at the boundary of biology and physics. Over the years, many theoretical and data-driven models have been proposed, some simple and some complex. These two examples are a data-driven fish school model and the fish shape model, which we will look at in a future video. Today we'll go as simple as possible and take our first step towards real-world behaviour by focusing on one particular model of active matter, the active Brownian particle, or ABP. Then we will build up to large groups of colliding ABPs. This simple model conceives of a particle able to move itself along a given direction. That's the active part. The Brownian part is in reference to the random motion of the particle's direction of travel. Apart from that, our particle has no other properties. Its shape, shown here, is arbitrary, since there is nothing in its environment for it to interact with. Later, however, when we add collisions, shape will be important. Typically, the ABP model is successful in microscopic applications, such as bacteria, vibrated particles shown earlier, and active colloids, which are fluids filled with insoluble small particles. Indeed, multiple variations and similar models exist. For example, run and tumble particles, which move along consistent, straight trajectories interspersed with large changes of direction. Run and tumble motion is seen more often in bacteria, like E. coli. Let's explore the ABP model in detail. First, we'll define the working parts, and see how tweaking them changes the behaviour. Then, we'll take a look at the particle's environment. After that, we've set the stage to add more particles, and we'll have to talk about collisions and interactions. Finally, we'll round off with a few experiments of our own, revealing complex behaviour even from a basic model, and see some real examples where the ABP model is applicable. Notice the particle is only able to move in 2 dimensions, as if on a flat sheet of paper. 3D is of course possible and not so different, but we'll stick to 2D for now. The arrow indicates the particle's direction of travel, along which the particle propels itself at a given speed. Typically, the speed is measured in radii per second. That is, a speed of 1 means the particle moves 1 radius in 1 unit of time. At a speed of 5, the particle moves 5 radii in the same unit of time. This of course applies to a circular particle. For different shapes, a different length will be referred to. We can increase or decrease the speed parameter to allow the particle to move further distances in shorter times, or vice versa. The direction of this propulsion fluctuates randomly across time at a given strength. This is angular diffusion. This is one way we control noise or randomness for our particle. Holding the speed constant and increasing angular diffusion means more erratic, less directed motion. There is also noise applied directly to the particle's position, spatial diffusion, jostling it like Brownian motion, as if it is colliding with many microscopic particles. Increasing spatial diffusion does not affect the heading direction directly, but does affect the path of the particle, making it more erratic. The faster the particle moves, keeping the diffusion constant, the more persistent the particle's motion is. Alternatively, keeping speed constant and increased diffusion means more erratic motion. With no diffusion, the particle maintains a ballistic trajectory. That is, its direction does not change. In In simple cases, these parameters are constant, though they can vary with time, or other properties, depending on the application. Continuing with a single particle, let's increase the complexity by placing it in a box. In particular, let's place it inside a box with periodic boundary conditions. This means the particle's position wraps around from one side of the box to the other as it crosses a boundary. That is, when crossing the left boundary, the particle continues from the right-hand side. If it crosses the top boundary, it continues from the bottom. The reason for this choice is to avoid boundary effects. If the particle collided with the boundary, this could have a large effect when we add many particles, muddying our interpretation. In this way, when we add more particles, interaction only happens between them, not the boundary. So any effects we see can be attributed to particle interactions only. To increase complexity further, let's add a second particle. Both move according to the same rules. That is, each move with the same speed and diffusion. When they are close enough, they collide. For simplicity, the particles obey an excluded volume interaction. That is, they do not bounce off one another, simply not overlapping and continuing the same heading direction. Other than excluded volume collisions, the particles do not interact in any other way. Now we understand the working parts, let's examine a large system. Let's conduct an experiment by putting 1,000 particles in a periodic box. The colour represents how densely packed particles are. The brighter the colour of a particle, the more particles are near it. Remember, all particles obey the same rules, collide when close enough, but do not interact in any other way. For now there is no spatial diffusion, and we'll keep the rotational diffusion low. Let's watch what happens. What we have witnessed is the natural formation of a cluster. Further, a clustered or dense region living alongside a sparse region, a liquid and a gas. In jargon, this is called motility-induced phase separation, meaning the particles have separated into clusters due to their individual motion. What we can conclude from this is that randomly rotating particles, only interacting through collisions, can aggregate into clusters. When discovered in simulations like this, and in real-world examples, this was somewhat surprising, since it shows aggregation can happen without intelligent decision-making. But hold on, what happens with spatial diffusion? What about the size of the box, or the number of particles? These must have an effect. First, let's try 3 values of spatial diffusion: no spatial diffusion, moderate, and high. keeping all other parameters fixed: speed, angular diffusion, number of particles, and box size. Let's see what happens at these 3 diffusion levels. Notice the more jumpy and erratic motion as diffusion increases, and also how more spatial diffusion appears to inhibit cluster formation. This experiment hints that the clustering is an intrinsic part of an active system. As spatial diffusion increases, the particles behave more like Brownian motion, like pollen grains under a microscope, a passive system, as the self-propulsion is dominated by the thermal noise. Next, let's vary the box size. What happens if it's smaller or bigger? Again, let's try 3 values: large, moderate, and small boxes, keeping no spatial diffusion and the same number of particles in each box, etc. Notice that the largest box does not form large clusters. The medium-sized box forms somewhat larger clusters, but still not as large as the smallest box. This shows us that it's not just collisions and random rotation, or spatial diffusion, but density that's important for cluster formation. That is, with more space to move around in, it's more difficult for particles to get stuck in clusters. The importance of density will also show when there are fewer particles, of course. Before finishing, let's review some real-world experiments where this and other behaviour is seen, and where the ABP model is applicable. First, a broad class of experiments look at active colloids. Active colloids are suspensions of active particles in a fluid. The active motion of the particles is driven in many ways. For example, particles with partially exposed cores react with the suspension medium dependent on exposure to light. Or laser-activated Janus particles made of silicon dioxide spheres with one hemisphere coated in graphite. Laser illumination of an entire sample creates a heating effect on the carbon sides of particles only, giving self-propulsion. At a larger scale, about 1 centimetre, vibrobots, discs with angled legs, can be driven by use of a shaker on which they sit. The design of the legs converts the shaking force to forward motion. Biologically important examples are E. coli and spermatozoa, although there are more complicated factors in their motion, and are better modelled by the closely linked run and tumble particle, and other variations, accounting for the more complex biology. In this video, we looked at one very simple case of active matter and group level motion. It's our first step in complexity to understand real examples. In future, we will dive into more realistic models like boids and data-driven approaches, which have much more exciting behaviour. If you've made it this far, thanks for watching. I'd value your feedback via like or subscribe, or comment what you thought about this topic. So this is the first of what I'm calling deep dives. The idea is to present an introduction to a model with some, hopefully pretty visualizations. This video is mostly focused on concepts rather than maths or code. I was thinking, as well as moving on to other topics, I might do a video just about the code. So what does your basic ABP look like in code to start with? But also maybe optimizations like quad trees or octrees, and even GPU acceleration techniques. If you've got any opinions on this or other suggestions, I'd love to hear from you in the comments.